I discovered Ettore Majorana when I started studying physics. They told me about him and described him as a super genius, a sort of absolute physicist, of the same caliber as Galileo or Newton. Although he always preferred to remain out of the spotlight, he became famous in the European scientific world in the 1920s. But on the evening of the 26th of March 1938, he set off for Naples aboard a ship from Palermo and vanished into thin air. His body was never found. He was 31 years old. What happened to him? The only thing we can be sure of is that he orchestrated his own disappearance, that he intentionally covered his tracks so well that, to this day, nobody has been able to solve the mystery. In today's world, 80 years after his disappearance, some of his most fascinating theories are still relevant. One of them describes the existence of new types of particles, called Majorana particles. Do they really exist? Physicists still don't know. The detection of these particles may help unveil some of the mysteries of the universe. This is why they have become a major consideration in physics research. In our collective memory, Majorana's disappearance took precedence over his work as a physicist. So I have decided to tell my students about his revolutionary ideas regarding elementary particles, especially neutrinos. We're interested in them because they may help us to get to the bottom of some huge cosmological enigmas. The first enigma is that of antimatter. Why did antimatter disappear? Why did matter prevail over antimatter? And the second enigma is dark matter. This enigma of dark matter is what brought Majorana into the limelight. But what is it? Observing galaxies has sowed confusion for decades. According to the laws of gravity, the further a star is from the center of a galaxy, the slower its rotational speed. But that's not what we find today. Star speeds practically don't slow down at all the further they are from the central point, as if the mass acting on them is greater than the visible mass. What is this extra non-luminous matter called dark matter made of? Nobody knows yet. But if Majorana's theories were to be confirmed, it would help identify the nature of dark matter. I wanted to follow Majorana's footsteps, not just because I was intrigued by his disappearance, but also because his research fascinates the physicist in me. I decided to meet some members of his family, search through the archives, and try to figure out how he came across his neutrino theory, and maybe even understand the reasons why he chose to disappear.
The last time I was in Paris, I received a letter from Ettore Majorana. Without knowing that he had a nephew, I thought that it was he himself who had written to me.
How could you possibly think that? Come in, sit down. This is the thesis.
That's the thesis he put forward in 1929. Wow, that's incredible! It's about the inner mechanics of the nucleus, the mechanics of a radioactive nucleus.
Have you noticed how clear his writing is?
Incredible.
It's very precise.
3 sections. Bibliography, there isn't much here. I guess that's because they were just discovering these things. That just goes to show that they were researching in uncharted territory. It's typewritten though. Apart from the Greek characters. Alpha particle. The alpha is written by hand.
Have you seen this document before?
No, I've never seen it. I've heard about it. It's quoted in many books, but I've never seen the original document. There aren't many calculations up to this point, which is quite surprising from Majorana.
That's the introduction.
Here we go. Yes, now that looks more like Majorana. We're in the thick of the equations. It's incredible.
There's a very interesting comment. He writes, "Physics intuition completely justifies such a transgression against mathematical rigor."
From as young as 23, he already considered himself as more of a physicist than a mathematician, even though he was an excellent mathematician.
Indeed, he mastered mathematics perfectly, but he was also aware of its limitation. And he knew how to use maths in physics. In some ways, he represented the new face of theoretical physicists, which there weren't many of in Italy. I'll show you some photos. They're beautiful.
There. Is he there?
That's at the house. That's Gaston Piquet. They were friends from university.
There are lots of bottles of wine.
Well, naturally. That's my dad. Majorana was very serious.
They all look drunk or happy. And then there he is, behind them, looking very serious.
He'd drink with them, but very seriously.
This one must be a post-graduation party, because one of them is brandishing his degree. And Majorana is at the front, smiling a bit.
Did you notice his hard stare? He looked determined, aggressive, almost aggressive, proud.
Proud. This is incredible because it's the only photo that I know of where you see him really laughing. He's not smiling, he's really laughing. He seems very happy.
He was enjoying himself. Trips to the countryside by car.
So Majorana was a very social being.
Absolutely.
He's always described as being a solitary misanthrope, but he actually spent his time having fun with his friends.
Yes, while he was at engineering school. Then he joined the Institute of Physics, and his mood began to change.
Did he become introverted when he got into physics?
He was very focused on science. Before that, he was definitely thinking about physics and science. But then, he became a creative spark in the world of science and absorbed everything. In reality, I think Majorana's drama was an internal drama. He was full of energy and very intellectually alert. Majorana was very gifted, but he was also a normal person. We know that anyone can have their own internal drama.
To learn more about Majorana the man, I wanted to visit the place where he had lived, in the hope that he would stop evading me. Because Majorana was a bit like the particles he theorized, discreet, enigmatic, and untouchable. I thought it best to start in Catania, his birth town in Sicily. Back in the day, in 1906, physics was experiencing a major revolution. Albert Einstein had just developed his theory of relativity, and Jean Perrin had just proved the existence of atoms through his experimentation.
This is where it all started for Ettore. But in reality, things started much earlier. You have to think back to that period in history. Positivism. At the time, Catania was a very lively city. People were looking at the world in a new way, a world that was about to undergo profound changes. So that was the environment that Ettore was born into. My Aunt Dorina, his mother, was a housewife. She looked after the house. But she was a very important woman and very close to her kids. She was rather domineering.
A Sicilian mother.
Yes, a Sicilian mother. Her father, Fabio, was a great engineer who built extraordinary buildings of exquisite beauty.
I've been told that sometimes, when the Majorana family had guests, or friends or family staying, they'd ask Ettore when he was 3 or 4 to do complicated calculations, and he'd go under the table to hide, and he'd tell them the correct answer because he was very good at mental arithmetic, but he was already hiding himself away. Is that true?
For me, the most important part of that story, which may be true or just a legend, I don't know. It's the idea that he was hiding under the table, because it shows his shy side and his desire to remain hidden.
Hello.
Hello, Fabio.
Careful on the steps. The kids used to play with a donkey here. They'd climb with the donkey.
Hello. I'm thrilled to see the Majorana house where they spent their holidays.
Yes, they used to come here on holiday.
This house is no longer inhabited, but you can imagine there were lots of kids here, Ettore and his brothers and sisters.
Yes, his brothers, sisters and grandmother. The whole family came here.
He was born on the other side of Etna, but he spent his holidays on this side. He went back and forth over Etna.
Yes.
In 1915, Ettore Majorana was sent with his 2 brothers and cousins to a boarding school in Rome. He was 9 years old. How did the shy and lonely young Majorana spend his years far from the warmth of his family? Was this the source of his social isolation? It's difficult to say, because Ettore wasn't a sad child.
These are the letters he wrote while he was at college.
In Rome.
Dear Dad, I got Mum's letter. When will you come? We're all fine here. I haven't had any letters from you. How are you? You and Mum. Did Grandma come back? Will Maria come too? He wanted to know everything that was going on. It rains here a lot. Millions of kisses. Your loving son, Ettore.
You can tell he missed his family. He asks what everybody's up to.
There's a difference between who he was and who he wanted to be seen to be. He must have known this from early on in his childhood. Ettore Majorana didn't see the world as others see it. His black, glistening eyes seemed too present not to be a part of ordinary life. His gaze seems to go beyond the visible world. It wasn't until 1921 that his parents joined him in Rome. Majorana joined the Torquato Tasso College, one of the most highly reputed in the capital, which his brothers attended too. He achieved excellent grades. After completing his baccalaureate, he began studying at an engineering school in Rome.
So this is the engineering school where Majorana studied, is that right?
Yes, exactly.
He spent 2 years here, 2.5 years.
2 years in engineering.
Before he joined the Fermi team.
Yes.
Engineering school, physics, chemistry, maths.
They were great years as an engineering student. That was also the point where Majorana started taking an interest in physics. He was given the opportunity to attend a conference by Fermi, who was trying to bring all the best physicists together. Segre was the first, and naturally he invited Majorana.
I read quite an interesting story. It's about the first time Majorana and Fermi met. Majorana visited Fermi after he invited him. Fermi explained what he was working on. He was calculating a potential using quite a complicated equation. and for several days he had been trying to find the numeric values of this potential with a calculator.
Using a calculation of successive approximations.
Majorana saw what was happening, turned around and walked away without saying goodbye or what he was going to do. He came back the next day with all the potential values Fermi was trying to calculate written on the back of a cigarette box. He had worked them out all by himself overnight, using his own special mathematical methods.
It's as if he was asking, what results do you get? Fermi told him his results. Majorana confirmed, that's correct.
So it was actually Fermi who was being examined.
In some ways, yes. Majorana realized that there was a lot of competition in the group, and he didn't reveal how he had worked out the result overnight. It was a huge piece of work, fairly complicated, not straightforward, which he must have worked really hard on. He didn't explain anything. His aim was to assess the level of the group and impress them and show them that he was very capable. And then he just left, without explaining a thing.
So Majorana joined Fermi's team, and that's where the story began.
Yes, that's where the story of Majorana and physics began.
In Italy, where physics was a dwindling area of expertise, Fermi, who was only 25, introduced two new ways of seeing the world: quantum physics and the theory of relativity. Elsewhere in Europe, ideas were already bubbling. Other young men, Paul Dirac in England, Werner Heisenberg in Germany, and Wolfgang Pauli in Austria, were making fundamental breakthroughs. They understood that the world of the infinitely small is not ruled the same way as the macroscopic world. It escapes our senses and baffles us with its paradoxes and oddities. Fermi wanted Italy to make up for lost time. Mussolini, who was in power, set up the Via Panisperna Institute of Physics in Rome. Fermi adopted the role of manager with the aim of turning it into an internationally reputed research centre. I had to find out more about Fermi and his team of young, enthusiastic men whose discoveries would go on to radically change the face and power of physics. I met up with Giuseppe Mussardo, a theoretical physics professor at Trieste and great friend of Majorana and Fermi.
I've been told of a restaurant where Fermi's team often came to eat. Do you know which one?
Yes, there were several restaurants, including this one. If you want, we can go in and I'll show you. The Via Panisperna Institute was a historical institute for Italian physics. It's where Fermi put together his incredible team, which is known as I Ragazzi di Via Panisperna. It was a very dynamic institute. Fermi made it dynamic. They'd meet up in the afternoon. He would tell them about the latest theories that were coming to light in the international community, and they'd start work. And back in the day, these theories would circulate among scientific circles by letter or by postcard, aboard trains or boats.
Majorana wasn't like the other physicists. What was so different about him?
Majorana was a pure theoretical physicist. He was distinguishable from others due to his ability to abstract and his critical mind. His personality earned him the nickname the Great Inquisitor. All the members of the group had nicknames. Fermi was the Pope, the one in control. Franco Rossetti was Cardinal Vicar. Segre was the basilisk, due to his cutting retorts and venomous personality.
Did Majorana get involved with the collective life of the group?
Majorana was quite a unique person. He didn't really take part in the group. There's an anecdote from Laura Fermi, Enrico Fermi's wife, in her book Atoms in the Family. She describes how Majorana has his own special way of participating in group discussions. For example, if Majorana came up with a problem that might interest the group, He'd arrive in the morning, go straight to the board, start discussing the subject and get out his packet of cigarettes, which he'd written formulae on. He wrote them on the board and then he'd scrunch up the packet and throw it away. He didn't publish anything.
But although Majorana hardly published anything, he wrote thousands of pages of calculations, which have been kept at the Domus Galileina library in Pisa. I couldn't wait to see them and look at all the books he'd left behind as a way of entering his thought process. The thing that really moved me was to be able to touch these little treasures that he'd once handled himself, with my own bare hands. To this day, researchers still refer to it in the hope of finding new ideas or inspiration. In terms of scientific output, 1931 and 1932 were miraculous years. He was 25 and people were already talking about his innovative ideas both in Italy and abroad. His reputation grew so quickly that his destiny escaped him. Majorana had the gift of being able to use the concept of symmetry to describe physical phenomenon. After his disappearance, other physicists pursued his theories, which led to the discovery of Higgs boson in July 2012 at the CERN, a crucial discovery that contributes to our understanding of the origin of mass of subatomic particles. It was during this miraculous period that Majorana wrote an article, which was rapidly distributed and went on to become one of the most cited articles in history. It was called Atoms Orientated in a Variable Magnetic Field.
So how was the atom being represented by the end of the 1920s? Well, we know that there's a nucleus at the center of an atom, a big N, which electrons revolve around, just one if it's hydrogen, or more than one if it's any other chemical element. So an electron can travel, for example, around this orbit, or this one, or even this one. The most important thing is that there are orbits that electrons are allowed to travel along. And between those, there are orbits like this one which they can't travel along. So, not all the orbits can be used by the electron. If an electron travels along an authorized orbit, quantum physics says or postulates that it won't emit light. However, electrons can emit light in the form of photons as they shift from one orbit to the next. And so the photon energy emitted is equal to the difference in energy between the starting point and the end point. As such, if you were to place the different possible electron energy states on a scale, you'd have an energy that corresponds to this orbit. For example, another energy that corresponds to this one, and a third one that corresponds to this one, etc. So we get a spectrum of energy that looks a bit like a set of stairs, where each of the steps corresponds to an orbit that the electron can travel along. When the electron changes orbit, it passes from a certain energy level, like this one, to a lower energy level, or to an even lower level, and each time a photon is emitted, the energy of which is equal to this difference. So if we look at the total frequencies emitted by the atom, which we refer to as its spectrum, we'll see that the frequency affects the number of rays, and each ray corresponds to a possible transition in the spectrum that I just drew. What Majorana explains in his article is that if you put atoms into a variable magnetic field, these rays will extend under the effects of the magnetic field and almost split in two. And we call this the Majorana-Brossel effect. Brossel is the name of a French physicist who demonstrated this phenomenon in 1955 and marks the beginnings of magnetic resonance imaging.
But Majorana didn't stop there. His main research involved subatomic particles. He found the equation that would enable us to describe them in any circumstances, using both principles of relativity and those of quantum physics. It was a pure theoretical masterpiece and only 9 pages long. But his peers struggled to understand it. The methods he used were too innovative. This article, written in 1932, was laid to rest for 35 years before it was rediscovered and revived, much like Sleeping Beauty. Majorana, who had very little life experience, had theorized like no one else, and not just in the world of physics. I met one of his other nephews, who lives in the same building the Majorana family lived in, on Margherita Street in Rome.
Ettore was interested in everything. As far as I know, he regarded everything around him from a holistic standpoint. Because he didn't start out in physics, he came from a classic college, and physics just gave him possible answers to the way he studied reality.
Can you give an example of a situation where he tried to show how physics might explain other scientific disciplines, for example, social sciences? I know he wrote on that subject.
Definitely. It's not too emotional.
It could be risky. Let's see.
Well, this here is Ettore's original social science manuscript.
Thank you. I'll translate. The value of statistical laws in physics and in social sciences. In any case, you can see that he has combined physics vocabulary with social sciences vocabulary. He talks of free will, individuals, he talks about atoms.
Absolutely.
He discusses the law of large numbers. It's the idea that individuals in a society are not equivalent to atoms, because they have free will. They can make decisions, and that quantum physics and its indeterminacy is more relevant than conventional physics when it comes to social sciences.
In the introduction, he begins with conventional physics and the meaning of statistics in conventional physics. And gradually, and by addressing the issue of entropy, he moves on to the subject of indeterminacy. It's quite possible that as he started studying quantum physics, his horizons grew broader and he started doubting.
So, he had an all-encompassing perspective from which he sought to bring together all scientific, mathematical, and philosophical knowledge into one movement in order to form a project that would lead us to the truth, right?
I think he was less a physicist and more a universal person, with a universal mind, and he chose physics as a tool to try and understand the only reality.
On the 18th of January 1932, a momentous event took place which completely turned Majorana's subject of research upside down. In order to identify the nature of the radiation that had been recently discovered in Germany, Irene and Frederick Joliot-Curie directed it at a target and noticed that this type of radiation was able to displace protons. They interpreted this new phenomenon by explaining that the radiation in question must be made up of light containing high-energy photons.
A few days later, Majorana was in the library. He took the French publication, written in French, read it, and once he'd finished reading the article, the other people in the room heard him say, "Stronzi," which in Italian means idiots. They had discovered the neutron without realizing it. What Majorana understood was that this radiation wasn't light, it was neutrons. But until 1932, until that time, this is what physicists believed the nucleus looked like.
Physicists believed that the atomic nucleus was made up of protons and neutral protons, the neutral proton being a proton and an electron that were bound together. As far as they knew, atomic nuclei only contained two sorts of subatomic particles, protons and electrons.
The proof is that there already existed a phenomenon called beta decay, by which nucleus A is able to become another nucleus by emitting an electron. For example, the initial nucleus may be potassium-40, which becomes calcium-40 with an emitted electron. So what does that mean to a scientist? An electron is able to leave a nucleus. If a particle is able to leave a structure, it means the structure already contained the said particle. Okay, if you pull a rabbit from a hat, it means that the rabbit was already in the hat, which we call the toothpaste argument. The paste that comes out of the tube was in the tube before it left. So, if electrons are able to leave a nucleus, it means that there were already electrons in the nucleus. So that was the accepted line of reasoning up until 1932. And Majorana was the first to understand that the radiation the Joliot-Curies had discovered, or the effect the radiation produced, was the neutron. And neutrons are subatomic particles, much like protons.
An atom's nucleus is actually only made up of neutrons and protons, without electrons. So Majorana understood that a different force was at play, a nuclear force, which caused protons and neutrons to interact strongly with each other within the atomic nucleus, and he came up with a revolutionary theoretical model.
It was a fantastic theory. Fermi urged him to publish it, or at least present his theory to the conference, which was to take place in July 1932 in Paris. But Majorana refused. Fermi went to the conference in Paris. That's where he met Heisenberg. And Heisenberg, on the 19th of July 1932, published an article that practically detailed Majorana's very own theory. Fermi was shocked. He pushed Majorana to publish the article again. But Majorana refused, saying that Heisenberg had already explained everything, maybe even too much. Despite everything, Fermi convinced Majorana to go abroad. He got him a study grant. In January 1933, Majorana joined Heisenberg's team in Leipzig.
But in 1933, it wasn't just physics that changed course. In Germany that January, Hitler was appointed Chancellor, suspending the constitution and investing all the country's machinery. Could this political context have scared Majorana? He doesn't mention it much in his letters, but his perspective seems complex and ambiguous. On the one hand, he seems worried about the rising Nazism and anti-Semitic laws, and on the other hand, he thinks that the country's economic policies are on the right track. During this time, the Institute of Physics in Leipzig had become a hotspot for theoretical physics. Majorana and Heisenberg's friendship grew strong. Their discussions touched on philosophy as much as they did physics. This was no doubt the happiest part of Majorana's life. Together in the Zeitschrift für Physik journal, they published an article on the structure of atomic nuclei, in which Majorana corrected and improved Heisenberg's model. This paper is one of the founding texts on nuclear physics. Majorana's stay in Germany was interrupted from the 5th of March to the 12th of April 1933 by a visit to the Niels Bohr Institute of Physics in Copenhagen, where young and enthusiastic theoretical physicists who spoke various languages were joyfully involved in the twists and turns of these two new continents, the atom and its nucleus. Once back in Leipzig, Majorana seemed less passionate. His relationship with Heisenberg did not seem to have been as profound as he would have hoped. Even with the greatest minds, Majorana, like many other geniuses, seemed condemned to solitude.
Majorana came back to Italy on the 5th of August 1933, on his 27th birthday. He was a different man, much sadder, more melancholy. He'd become introverted. He didn't see his friends anymore. He didn't visit anyone. He was a man who was definitely going through a difficult stage in his life.
Is there a way of understanding this change in character? Was it his work on nuclear physics with Heisenberg that made him scared of physics, and therefore the atomic bomb that made him decide to stay away from the world of research?
The issue of the atomic bomb was heavily debated. Years ago in Italy, a very violent debate was started by Leonardo Sciascia, a major Italian author. In one of his books, he suggested that Majorana's unhappiness was due to the fact that he knew what science might lead to. It seemed very unlikely that Majorana could have anticipated the events that occurred.
This period in Majorana's life remains shrouded in secrecy, and all the research I've done about it have been doomed to failure. In any case, from that moment on, his life changed forever. Majorana was never the same again. His name gradually disappeared from the academic world, in which he occupied no official position. Majorana was no longer cited in any seminar reviews or any scientific publications. This withdrawal lasted 3 years. In 1936 he started getting better and stopped living as a recluse. He started working enthusiastically on a quantum formula for the laws of electromagnetism. In early 1937, the ragazzi di Via Panisperna told him that a position as a professor had just opened up in Palermo, as arranged by Emilio Segre, who was already teaching there. But in order to apply for the position, knowing that he hadn't published much, he'd have to present some recent research. He picked up on the work that he'd started during his stay in Leipzig, and within a few days wrote what would be his last and most prophetic article: A Symmetrical Theory of Electrons and Positrons. It was an alternative to Dirac's theory on antimatter.
So in 1928, Dirac wrote his equation, which was both quantic and relativist. And he was astonished to find that his equation led to solutions corresponding to negative energy particles. In 1931, Dirac finally produced a new interpretation of these negative energies by saying that vacuums are in fact full. The idea that led Dirac to this conclusion actually involved fish. If you imagine a fish in very deep water which never comes up to the surface and will never go all the way to the bottom of the ocean, so it's constantly between the two. It often sees objects flow past it. The fish, let's assume that it has basic intelligence, will eventually realize that there must be a force to play that pushes all these objects in the same direction, downwards. Having seen these objects fall, he thinks, okay, there's a force pulling things to the bottom. I'll call it gravity. And let's say that these falling objects have a positive mass, which is what pulls them towards the field of gravity. And then one day the fish sees an empty bottle fall, but there's a bit of air stuck in it. The bottle hits the bottom, and as it hits the floor, the air bubble gets released on impact. The bubbles escape and rise to the top. What does the fish make of this? That these bubbles seem to do things the opposite way because they move in contradiction to ordinary objects. In brief, it seems as if they have an opposite mass, in other words, a negative mass. Dirac's idea was that a negative energy particle is the same as an antiparticle of positive mass. That's where Dirac's idea of antimatter came from. And it turned out that Majorana didn't agree. He said, "I don't believe this Dirac sea theory. I don't believe in negative energies." And so the paper I'm referring to started with this sentence: "I reject Dirac sea." He wrote an equation that looked like Dirac's. However, if a particle has a zero charge, it may be identical to its antiparticle. And so the question at hand is the one I raised in the introduction. Is Majorana's equation for antimatter correct, and not Dirac's? So the question is, are there particles that are their own antiparticle? Of the particles that we're aware of, there's only one that could possibly fill this role, the neutrino. We have now known for 15 years, after the 2002 Nobel Prize, that neutrinos have a non-zero mass. We don't know their mass, but we know that it is non-zero. As such, it becomes essential to know whether Dirac or Majorana was right.
Experiments all over the world, at the Gran Sasso in Italy, the Super Nemo in France, and the Super Kamiokande in Japan, are all trying to establish whether Dirac or Majorana were right about neutrinos. According to Dirac, neutrinos are separate from their antiparticles. To the contrary, Majorana believed that they are identical to their antiparticles. Who was right? A good way of proving that Majorana was right would be to demonstrate a phenomenon that has never been observed. Double beta decay without an emission of neutrinos. Classic double beta decay is the process by which two neutrons transform into two protons by emitting two electrons, causing two neutrinos to leave the nucleus. If Majorana was right, then there should be cases where both neutrinos annihilate each other, the first acting as the antiparticle of the other. So will we only ever see two electrons leave the nucleus and not neutrinos? If this physical process were to be detected, it would have a huge impact. On the one hand, it would show that Majorana's particles exist, and that some of them may form dark matter. On the other hand, it would force physicists to establish new laws that would help them explain how matter prevailed over antimatter in the creation of the universe. More particularly, it would mark the start of a new era for physics. Majorana was like no other theorist. Is it possible that he was intelligent enough to solve a major problem before it even became one, and at a time when the words used to specifically describe it didn't yet exist? So what frame of mind was he in a few months before he disappeared, as he presented his antimatter theory to the jury in the hope of becoming full professor of theoretical physics at Palermo University? Despite Fermi sitting on the jury, Majorana did not get the position in Palermo. However, on account of his exceptional expertise, they specially created a full professor position for him in Naples. Majorana, who did not like public speaking, spent his final 2 months giving lessons to students, but only 5 of them with whom he was very attentive. I was curious to meet Professor Salvatore Esposito at the Institute of Nuclear Physics in Naples. I was sure he could tell me a little more about Majorana's last days before he disappeared.
First of all, he was visited by a very well-known physicist at the time called Occhialini, who came to visit him here at the Institute. How did that go?
Occhialini had wanted to visit Majorana for a long time, but he'd never had the chance. At the end of January, he returned from Sao Paulo in Brazil. His boat stopped here in Naples for a few hours. He used his time to visit the Institute of Physics. He said to Majorana, "It's odd that we should meet upon my return from Sao Paulo when I used to live in Florence." And Majorana rather curiously replied, "You got here just in time. If you'd come 2 or 3 weeks later, you may not have found me."
Perhaps that means that he had intended to disappear since January.
At this point, he was probably planning his disappearance, and until 25th of March, he spent his time carefully planning it.
So I went to Pisa and I took some notes, because that's where there are two letters that Majorana had written on the 25th of March. There's one that he left in his hotel room for his family, which says, "I only wish one thing, that you do not wear black. If you want to respect tradition, wear a sign of mourning, but for no more than 3 days. Then, if you can, hold me in your hearts and forgive me." And then there's a letter that he wrote to Corelli, the director of the Institute, who was his colleague here in Naples. "I made a decision that has become unavoidable. There isn't a bit of selfishness in it, but I realize what trouble my sudden disappearance will cause you and the students." He then goes on to say that he's taking a boat for Palermo that evening at 10 p.m. "I will keep a fond memory of them all at least until 11 p.m. tonight, and if possible, even after that."
2 very mysterious letters. On the one hand, they point towards suicidal intentions. On the other hand, they point to another possible solution, probably to give hope to his mother, who would be left alone.
I wanted to take the same journey, on the same day, at the same time. To understand why Majorana went to Palermo and put myself in his place to try and find an explanation that no one else had thought of. I tried to imagine the mindset he would have had on the 25th of March 1938. Maybe he felt the serenity of those who, after deep suffering, know that their decision has been made and that soon it will be over for good. But I couldn't help but think that the last 3 traces Majorana had left were rather strange. First of all, why Palermo? To meet his friend Segre? He had left for the USA. Did Majorana not know? And in his letter to Corelli, what does he mean by "and if possible, even after that"? Did he want to take the memories of his loved ones with him in death? Or was his decision not as irreversible as he had written? In any case, on the morning of the 26th of March 1938, he arrived in Palermo. From there, he sent Corelli a telegram to tell him not to be alarmed by the letter he was to receive. Corelli didn't understand what was going on. At 2 p.m. he received said letter. Majorana had posted it from Naples a few hours before boarding the ship. On the 27th, Corelli received a third message, written on paper with a Hotel Grand Albergo Sole Palermo letterhead, which had been posted via express delivery a few hours after the telegram. "Dear Corelli, the sea rejected me. However, I have the intention of giving up teaching." The sea rejected me. What a mysterious phrase. Did his plan to jump overboard fail? Did Majorana want to make another attempt on his return journey? This letter is the last tangible trace of Majorana's life. On Monday, 28th of March, he did not turn up at the Institute, nor at the Hotel Bologna where he was staying. Corelli was distraught. On the 30th of March, he alerted Fermi, who immediately wrote to Mussolini, even though he'd never felt any sympathy for him. He begged him, as testified by the note from the Italian Ministry of the Interior, to do everything you can and quickly to find Ettore Majorana as discreetly as possible, who he then described as height 1.7 meters, long face, big wide eyes, black hair, dark complexion, iron grey overcoat, dark brown hat. Following their investigation, the police concluded that Majorana had made the return trip, but without absolute proof of his presence on the ship. Weeks went by and all searches and efforts to find him remained in vain. There was never a living sign of Ettore Majorana ever again. People have come up with several hypotheses regarding his disappearance. He committed suicide. He took refuge in a monastery in Calabria. He left for South America, or even that he was kidnapped by the Nazis. Is it true? Is it false? It still remains a mystery. All these questions remain unanswered, much like Pirandello's Matthias Pascal, who could have left his hat and jacket with a letter in the pocket on the parapet of a bridge over the river. And then instead of jumping into the water, he just walked on elsewhere. It is time for me to leave Majorana's mystery alone, and to tell myself that it was as if he annihilated himself, as if he was his own antiparticle, as if he tested his antimatter theory out on himself. In short, as if he became a genuine Majorana particle.